Welcome to Deriving and Solving Literal Equations. Many important mathematical facts are expressed in the form of equations or inequalities relating to or more variables. For example, the coordinates x, y of points on a line will always be related to each other by an equation in one form or another. Here's one form, ax plus by equals c. That's the standard form of a linear equation. But you also know that there are other forms like y equals mx plus b. In this lesson, you will learn how to manipulate equations in order to solve for a given variable. So for example, in that linear equation, if you wanted to write it in a different form, you can just move things around from one side of the equation to the other. And that's just manipulating or solving literal equations. You will also learn how equations can be used to prove important principles in math. So we can take equations and we can rewrite them or change them or use substitution in order to create another equation that solves or proves some principle in algebra. Our objectives are to explore ways that reasoning with equations can be used to prove these important general principles, and we're going to practice solving literal equations. All right, mathematical work often requires solving linear equations given in different forms, as we talked about earlier. Maybe we want to find formulas that give intercepts or slope of any line. That our equation is in this form, ax plus by equals c. Well, we might begin by reasoning as follows. So in this case, what we want to do is actually find an equation that gives us our x and y intercepts. So we could say that the y-intercept point has coordinates in the form of 0, y. Now think about what this is. Because if we have an axis, and here's our axes, any point here on the y-axis will always have coordinates 0, some y value. And what we're trying to figure out is what that y value is. So we can use that knowledge to help us derive an equation. So given this general form, ax plus by equals c, if we plug a 0 in for x, so we're substituting, then we can come up with something that will give us our y-intercept. Well, a times 0 is just 0. So remember, anything times 0 is 0. We're left with by equals c. We haven't yet solved for y. We need to divide both sides by b. b divided by b turns into 1, which leaves us with 1y, which is what we want, equals c over b. There's a general equation to help us. Let's do the same thing with the x-intercept. Well, again, if we're looking at the x-intercept over here, what is our y value? Our y value is always going to be 0 as well. So whenever we're trying to find the x-intercept, we know it's always going to be x, which is some number, 0. Let's do the same thing. Let's plug in a 0 in place of y, and then let's figure out an equation. Well, b times 0 is gone, that's just 0. So we're left with ax equals c, and we need to isolate the x in order to give us the x-intercept, so we'll divide both sides by a. That leaves us with x equals c over a. Now let's try out these two equations and see how well they work. Here is a linear equation in standard form, 4x minus 7y equals 12. Let's see how it goes. Well, to find the y-intercept, we want to put c over b. Okay, remember where a, b, and c are. A is in front of the x, b is in front of the y, and c is by itself, the constant term. So y is c, which is 12, over b, which, be careful, is negative 7. There's our y-intercept. Let's find our x-intercept. Well, our x-intercept is c, which is 12, over a, which is 4. We can simplify this one because 12 divided by 4 is just 3. We found our x and y-intercepts with hardly any work. So if you are working on a bunch of equations and you need to find x and y-intercepts, you have something that you've created, a tool, in order to help you do that. We can do the same thing with the slope, but that would require us to actually rewrite the equation. And we're going to look at that in a few minutes when we solve little equations. All right, let's look at deriving equations. Recall the Pythagorean theorem. It relates the lengths of the legs and the hypotenuse of any right triangle. And it says that if A and B are lengths of the legs, and C is the length of the hypotenuse, then we can say that A squared plus B squared equals C squared. This is important because this helps us to find lengths of the legs of a right triangle. All right, we're going to use this diagram to help us come up with a proof for the Pythagorean theorem. In order to complete our proof, we're going to go to A, write two different algebraic expressions that show how to find the area of the large square. Using our diagram, what can we do? Pause the video and see if you can come up with one expression that gives you the area of this whole thing. And then come back and we'll do it together. The first way is pretty easy. We know that length times width, in a case of a square, it's length times length because they're the same, will give us the area. So if we look at the length, we have two numbers. We have this part, which is B, and this part, which is A. We need to add those together. So we can call that B plus A. And then the other side here, so length times width, is also B plus A. That is equal to our area. But we could probably simplify this, right? We have multiplication. In order to multiply, we need to distribute. So we would take B times B plus A, and then A times B plus A. Some of you know this as FOILing, but it's really the distributive property. If we do that, B times B is B squared. B times A is AB. And then A times B again is AB. And finally, A times A is A squared. This is our area. All right, let's write another one, but this time, let's use the fact that we have four triangles on the inside and we have a square. So once again, pause the video, see if you can come up with an equation for area using those four triangles and the square. All right, well, if you'll notice, we have four of the same triangles because each of the base and the heights are A and B. So we have 4 times A times B divided by 2. Remember that the equation for the area of a triangle is length times width divided by 2. So A times B divided by 2. But then we have 4 of them. Plus, we have this square on the inside. So if we multiply the base times the height or the length times the width, however we want to say that, we have C times C, which is just C squared. Okay, we've created two different equations. Now in B, we want to equate these two expressions and apply our algebraic reasoning in order to show that we have A squared plus B squared equals C squared. So let's try that. Okay, think about what we have here. We have this whole equation, B squared plus AB plus AB plus A squared, which equals A. And then we have this equation, which also equals the area. Okay, so how can we combine all these together? Well, we can take this equation, which is A, and set it equal to this equation, which is also A. Let's try that. We have B squared, and now let's combine these two terms here, AB plus AB, because those are like terms. 1AB plus 1AB is just 2AB plus A squared equals 4. Actually, on this one, let's simplify this as well. If we have 4 divided by 2, that's just 2. So we can call this 2AB plus C squared. In order to figure out if this equals A squared plus B squared equals C squared, we need to combine our like terms and simplify. Okay, we have 2AB over here and we have 2AB over here. Because they're both ABs, those are like terms. So let's move over this 2AB and combine it with this 2AB. Well, what happens here? Both of these terms cancel, right? This one turns to 0. 2 minus 2 is also 0. So what are we left with? We are left with B squared plus A squared on this side, and on the right side we are left with C squared. And now we have derived or proven the Pythagorean theorem of A squared plus B squared equals C squared. And that was just one example of how we can use equations and substitution in order to derive other equations or prove theorems that we know about. Let's go ahead and wrap up this video by solving some literal equations. We talked about this a little bit at the start when we talked about the linear equation in standard form. But let's look at a couple of different situations. In this situation, we have Fahrenheit and Celsius. So this is an equation that converts Celsius into Fahrenheit. But what if we wanted to go the other way? What if we knew Fahrenheit and we wanted to determine what that was in Celsius? Rather than plugging in and constantly having to go through a long process, we can just rewrite this. First step in rewriting is to isolate C. So we need to move the 32 to the other side. And that would give us F minus 32, which is equal to 9 over 5 C. Now for our second step here to isolate C, we need to remove the 9/5. Well, we could do it in two steps. We could multiply both sides by 5, since this is division by 5, and then we could divide both sides by 9, since this is multiplication by 9. Or we can do it in one step, and we can multiply both sides by 5 and divide by 9 at the same time. If we do that, we have to multiply this entire left side by 5/9. Notice 5/9 is just the reciprocal of 9/5. 9/5 times 5/9 is just 1, and we are left with C, which is what we want. It's now isolated. And on the left side, we could distribute the 5/9 to the F and the 5/9 to the 32 by multiplication, or for simplicity's sake, we'll just leave this as 5/9 times our Fahrenheit minus 32. And that's a quick way to take our Fahrenheit temperature and turn it into Celsius. Let's look at this second example. We want to rewrite this to solve for T. Okay, without looking at what this is a quadratic, first of all. We don't know what it pertains to, but we can see that it's a quadratic. We can pull out our math knowledge, and we know how to solve for T in quadratics. We can factor, we can use completing the square, or we can use the quadratic formula. Remember that the quadratic formula says everything needs to be set equal to 0. In order to do that, we need to move the h to the other side. So we are left with 0 equals negative 5t squared plus 8t, and then we have plus 3 minus h on the end. One thing to point out is that this is our constant term, 3 minus h. We don't know what h is. It could be 5 or it could be 2, but this together is our constant term. Now what is this equation for? It says the height h of a diver over the water is modeled by the equation where h is the height of the diver and t is the time measured in seconds. So maybe in this case we want to know how long it would take the diver to reach a certain height, and we know the height. So we have a reason to rewrite it. So let's go ahead and solve for t. In order to solve for t, I'm going to use the quadratic formula because that's simplest and it gives us our solution right away. For the quadratic formula, we need to know that negative 5 is A, 8 is B, and the entire term, 3 minus h, is C. All right, let's give it a try. Negative b, that would be negative 8 then, plus or minus the square root of b squared, which is 64, minus 4 times a, which is negative 5, times c, which is 3 minus h, all over 2 times a, which is negative 5. All right, and there we go. We've solved for t. So all we need to do is figure out what h is, plug in our height, and we'll know how long it takes for this diver to reach this height. Our final one. This is the area of a sector, which is a pi wedge-shaped section of a circle, and it's given by this equation. R is the radius, and S is the angle measure of that sector in degrees. And we want to solve this equation for S. In other words, rewrite it in terms of A. Okay, we just take it piece by piece. First step is to move the 360 out of the denominator, which means we would multiply both sides by 360 since it's being divided in the equation. So we end up with 360a is now equal to pi r squared s. Okay, we're solving for s, so we just need to move the pi and the r squared over. Since this is all multiplication, we can divide all of these like this. These then cancel, And we have now solved for s, or rewritten it in terms of a. So s is equal to, and I forgot the little squared here, very important, 360a over pi r squared. That concludes our lesson today on deriving equations and solving literal equations. So my hope for you is that you can take an equation and use properties of algebra in order to rewrite it in terms of a different variable, and then also to understand that through the use and manipulation of different equations, we can prove important principles in algebra, geometry, and trigonometry.